essentially what we've learned so far can be condensed in one problem, a titration problem. Okay, this is it right here. It can be condensed to this. So what have we learned so far in acid-base chemistry? Well, what we've learned is that if you have a weak acid, you can calculate the pH, because that weak acid will dissociate. It's going to form hydronium ion, and you can calculate that hydronium ion by that shortcut um, technique I showed you. Okay, so that's one of the things that we've learned so far, is that if you have a weak acid, you can calculate the pH. We've also learned from our last discussion, okay, that if you have an acid and its common ion in solution, you can just go straight to the Henderson-Hasselbalch equation, okay? As long as you know the concentration of the acid and the conjugate in that solution, you can go straight to the Henderson-Hasselbalch equation. That's the other thing we learned. The other thing that we learn is salts. We know that if we have a salt, it breaks up into its ions. And now we can take that ion that forms and look at how it reacts with water. If you have something like sodium acetate, for example, okay, sodium acetate, you put it in water, it'll break up the sodium and the acetate. You can calculate the pH of that solution, because the acetate will react with water to form acetic acid. Why does it do that? Because it's the conjugate of a weak acid. Conjugate of a weak acid is a base. The base will react with water and form that weak acid again. Okay, that's so true of weak acids and weak base. They want to reform. They want to reform. So we learned that when we talked about salts. And then the last thing that you guys know, or maybe I didn't tell you this, but in the presence, if you have a strong base and you have weak base on top of that, a strong base in the presence of weak base, the pH of that solution is dictated by the strong system, the strong base. You don't even have to worry about the contributions from the weak system, because it's not going to add up. And we actually saw that in polyprotic systems. Remember phosphoric acid? Phosphoric acid, you have a system where it peels off one hydrogen, then that conjugate peels off a second hydrogen, and then that conjugate peels off a third hydrogen. But what was the concentration of the hydronium ion from that three reaction system? Well, the concentration all came from that first reaction, because the Ka from that first reaction was so much bigger than the Ka2 and the Ka3, that the contributions from the hydronium in the second reaction and third reaction was minuscule, So if you remember these four concepts, these four things that I talked to you about, you know how to do this calculations of titration curve. You know how to do that. And keep that in mind as we dive into this particular section. Okay, we're generating titration curve. You always know there's two components in a titration curve. There's actually more, but two major components, two major players, okay, in the titration curve. The first one, oh, here's the picture already. The first one is the analyte, okay, analyte. And the second one's the titrant. If your titration curve starts below 7, then remember, you are monitoring the analyte. You're looking at that with a pH meter. If your pH is below 7, that analyte's an acid. If your titration curve is above 7, then that analyte's a base. Okay, this is where 0 titrant is added. Now, what will happen is that if you have an acid, it'll become less acidic and more basic, because the titrant that you're adding has got to be an opposite. Otherwise, you don't get a neutralization reaction. So eventually, what will happen is that you get to the equivalence point. That's where the moles of your acid and the moles of your base are equal. That's your inflection point in your titration. And then you get excess titrant, Where it plateaus will give you a rough idea of what concentration of that titrant is. Okay, but you know that your titrant is going to be a base because you're making the solution more basic. The pH is going up. Here, you know your titrant is an acidic because you're making the solution, as you're adding the titrant, more acidic. Where it levels off will give you a rough idea of what the concentration of that titrant is. So those are just things that you need to be aware of when you look at a titration curve. Okay, so there are 4 regions in a titration curve. One is where you just have the beaker and you've got your pH probe in there and you want to know the pH. That's just an equilibrium problem. That's just a weak acid or weak base problem. Okay, that's, like I said, that's why I talked to you guys in the beginning of what you already know. In this particular case, what you can do is, if we have a weak acid titrated with a strong base, you always want to make your titrant strong, okay, and opposite to your analate. Why? Because you can, that's what you can control. Why make it weak and make it problematic for yourself? I won't even give you that in an exam question because it's not realistic. I won't tell you, generate a titration curve of a weak acid, titrate it with a weak base. It's not realistic. That's not what we do in lab. So don't expect to see that in an exam, okay? Don't even see it in your MCAT question because that's not a realistic problem. What is a realistic problem is that you have a weak acid, weak base, you got some chemical and you're analyzing and you're adding some titrant that you can control. And that generally would be a strong acid, strong base. So when you have this and you add, this is 0 before you even start the titration, guess what? This, just cut to the chase right here. You just do this. You just use that equation. You get the pH right away, or at least you get your hydronium ion concentration right away. Okay? Before the titration start, just calculate the hydrogen ion of that analate using that equation. Okay? Buffers, super easy, because what will happen now is that you're going to add a certain amount of base into your analate, and some of it's going to get, some of it reacts. So what you have here is you've got the acid and its conjugate present in the same solution. Guess what? If you know these concentrations, then you can just do this. Just use the Henderson-Hasselbalch equation, okay? And that's going to be in the region where you've got both the acid and its conjugate present, and that's a very big region in the titration curve. Then you get to the equivalence point. We call that hydrolysis. At the equivalence point, all the acid is wiped out because you got equal amount of acid and the base. Guess what that acid converts to? It converts over to its conjugate. So now what you have is like the salt problem that I mentioned. If you know this concentration, then that chemical will react with water to form hydroxide and its conjugate. Hydrolysis. Remember I talked to you guys about hydrolysis last time? It says it's reacting with water. That's what when you neutralize all the acid and it converts over to its conjugate, that conjugate is the only thing left. But when we do our thought experiment, that now will react with water through hydrolysis. It's not a buffer. Make sure you know it's not a buffer. You can't use the Henderson-Hasselbalch equation. What you can do is this right here. And guess what? You're forming hydroxide. That's a Kb problem. And you can do this. Hydroxide ion concentration equals the square root of Kb times the concentration of that base. You can do that. Okay? But remember, when you're doing a titration curve, you don't want to plot POH. You want to plot pH. So what I will see a lot of times, this is what I will see a lot of times because you guys aren't thinking, okay? You don't want to do that. I need to erase this real quick. This is what I will see in a titration curve. You will do this. You have a very nice start. You know what that is. And then all of a sudden at the equivalence point, it drops all the way down. If you have a disruption in your titration curve and it goes up and it drops, the reason why it drops is because this is your pOH value and not your pH value. If you convert that to pH, it'll be up here. Okay, it'll be up there. So you're just doing mechanically without thinking. You're going to calculate the hydroxide ion concentration with that, but you want the pH. So calculate the pOH and then use pH plus pOH equals pKw. Okay. Then we get this right here. We get this right here. I need to clear my, when we have that right there, what will happen is that you're going to be adding excess base. All you have to do is figure out how much that excess base you have, the moles, and know, because the volume's constantly changing when you're adding titrant. Divided by the volume total, and that'll get you your hydroxide ion concentration. You can just calculate the pOH from that, and then calculate the pH from that. And you're done. Those are the 4 things that you need to remember when you do a titration curve. Not hard, guys already covered the fundamentals. You did. You already covered the fundamentals. You just have to string it together in one big problem. And yeah, the one big problem might be intimidating, but make sure you understand the little bits so that it's not intimidating. It's not intimidating. So let me clear this because I want to make sure that I review this for you guys. Okay. This is basically it right here. Okay. This right here would be a titration curve for this particular discussion. It looks like that. This point right here is that equation right there. Once you add titrant, this region right here, that's your buffer. Use the Henderson-Hasselbalch equation right there. This equivalence point right here, that's the inflection point. That's your hydrolysis. That's when all the acid converts over to its conjugate. That's this equation right there. Notice that these 2 equations look very near identical. But one's for hydronium, the other's hydroxide, because at the equivalence point, you've converted all the acid to its conjugate, and now the solution will be basic. Yes, the solution will be above pH 7 in this particular case. Because remember, when we have a salt, if you have a salt made of the conjugate of a weak acid, the solution is going to be basic. Look it up. We talked about that last time. And then this right here, that's just the hydroxide ion concentration that is in excess. It's just a hydroxide ion concentration in excess. So this is a spreadsheet that I generated. These are the functions in Excel, okay? It's in the lecture notes. So when I need to generate a titration curve, I have something like this, and everything's sort of mathematically based anyway. Let's take a look at this problem. Okay, I've got about 15 minutes, so I'm going to somewhat summarize it for you. In this particular problem, I have, this is the titration curve. Notice this is region 1, this is region 2, this is region 3, this is region 4. Those are the 4 types of calculations I showed you. So that's what we are looking. That's basically what we talked about last time. So this problem right here is a titration where I have potassium hydroxide is my titrant, and hypochlorous acid, HOCl, it's a weak acid, okay? If I didn't give you hypochlorous acid, suppose I trick you. Not that I would, but if I did, and I made this HO2,3Cl, guess what that is? That's H ClO3. Okay. It's not a weak acid. It's a strong acid. So all of the things that you see right here doesn't apply because this is a strong acid, strong base situation. Don't get tricked. That's why you got to remember it's 7 strong acid. If I gave you HClO3 or HClO4, there is no Kas associated with that. If I gave you HClO2, there is a Ka associated with that. HClO, this is it, HClO, there is a Ka associated with that. And then you have to go through this exercise that I'm talking about, okay? So the first question that you will usually see is that, okay, we're doing a titration. You know what the titrant is, it's a strong base, and you know what the analyte is, it's a weak acid. And I need to get the pH values at 0%, 50%, 95%, 100%, and 105% of the equivalence point. Well, the equivalence point is where the moles of the acid and the moles of the base are equal. That's the equivalence point. So I need to know what the equivalent volume is, because if I know what the equivalent volume is, then I know exactly how much titrant I'm adding to calculate the pH, because you need to know that, okay? So in this particular problem, let me move on. It says that my weak acid is, I've got 10 milliliters, 10 milliliters. Notice we're dealing with milliliters, so you're going to be dealing with millimoles, and it's 0.4 molar. Guess what? 10 times 0.4, that's just 4 millimoles. 4 millimoles. 10 times 0.4, 4 millimoles. Okay? And we have a titrant, KOH. It also has the same concentration, 0.4. This is a super easy problem because at the equivalence point, I would need 10 milliliters because at 10 milliliters of 0.4, I would also have 4 millimoles of KOH. So the equivalence point here, 100%, that would be 10 milliliters. That means 105%, 10 times 10, 105, that's 10.5 milliliters of KOH. 95% would be 9.5 milliliters. 50% is 5.0 milliliters, and 0 is just 0. So you just figure out what the equivalent volume is for your titrant, because that's 100%. And then if the question is, what is the pH at 75%? Take 75% and multiply by the volume at 100%. That'll give you the volume at 75%, okay? So this problem, it's not so difficult because then I would need to know the pH. This is the volume right here, and I would generate a pH here, and the volume would be, this would be the volume of titrant. That's not the volume of the solution though. Okay, the volume of the solution will vary, but the volume of titrant will be 0, 5.0, 9.5, 10.0, and 10.5. Each time you're adding it to 10 milliliters. So 0 plus 10 is 10. 0 plus 5 is 15. So the total volume here, V total, because remember your analyte is 10 milliliters. So this would be 10. This will be 15. This will be 19.5. This would be 20. This would be 20.5. Why is the total volume important? Because whenever we're dealing with equilibrium, it's molarity that we use, not moles. Moles is for stoichiometry, but when we deal with equilibrium, mass action expression, Henderson-Hasselbalch equation, it's molarity. That's why you need a total volume. And the total volume will constantly change when you're doing the titration. Okay, so this is our job. This is our job to calculate the pH of this. Okay, one thing you should know, this is a GIF. At 50%, pH equals pKa. 50%, that's this right here. I know the pH of that because I know that the pKa of this acid is 7.46. So that's going to be 7.46. I'm not even going to think about it. Why? Because according to the Henderson-Hasselbalch equation, when I have equal amount of the acid and its conjugate. That's at 50% titration. That's, let me say that again, at 50% titration, not 100%, 50% titration. You have equal amount of the acid and its conjugate. If they're equal amount, that goes to 1, log of 1 goes to 0, pH equals pKa. That's this region right here. pH equals pKa. Now I tell you this now, and you guys are going to forget. You're going to say here is where pH equals pKa. No, that's the equivalence point. That's where hydrolysis occurs. Okay, pH does not equal to pKa at the equivalence point. Only at a 50% point. 50%. So you know that 10 milliliters is 100%. 5 milliliters is where pH equals pKa. You guys are going to have to know this for lab. Okay, when you do your unknown. So I already got a point. I got some points right now because I've got data. Okay, so yeah, it's messy here, but that's how you're going to have to set this up. That's how you're going to set this up. This portion right here, that's just, well, let's take a look. Okay, let's take a look. At 0%, all I need to do is really this. H plus equals Ka times the acid concentration. I know the acid concentration was 0.4. I know that the Ka was, what was the Ka? 3.5 times 10 to the minus 8. And now I can calculate the hydronium. So here's my calculator. Let me just do this real quick without looking at the answer. And I'll show you that comes pretty close. Okay, comes pretty close. I'm going to take 3.5 to the 8 negative. I'm going to multiply that by 0.4. And then I'm going to take the square root of that. That number comes out to 1.18 times 10 to the minus 4. And then I'm going to take the negative log of that. So I get the pH. That comes out to 3.92. Took me less than a minute to do that. Okay, or you can go through the ICE table. 3.93 if you are really going to. I actually solved this using a quadratic, I think, but 3.969. That translates to 3.93. Oops. There it is. Okay, don't make it hard. It's not. I'm showing you all the shortcut I teach my analytical students, analytical chemistry students. Okay. These questions are all the same since 20 years ago. So don't make it hard. Don't like have a, don't get exhausted in your brain because it's not that difficult. Okay, here it is right there, 3.93. ICE table gave you the same thing. Same thing. Okay, so you got your first point and you got your second point right here as well. Let me move on. Okay, 50%. Don't even bother doing a calculation. You should know that already. Okay, but here it is. I'm going to show you the calculation anyway. Okay, 7.46. That's what it'll be at 50%. Okay, so again, it's not hard, but a lot of you make it hard. Then you get an ulcer because you're frustrated. Here it is. This is the Henderson-Hasselbalch equation. This is the ICE table. Gives you the same answer. Gives you the same answer. Now I've got a second data point. Second data point, okay? What happens at 95%? 95%. We're still in the buffer region. We're not at the equivalence point, but we're still in the buffer region. You have to do a little bit of calculation on this. You have to know what acid you have, and you need to know how much conjugate is formed. So you have to do this, okay? You've got the acid and you know how much base is added. The first part has got to be stoichiometric because the base is going to dictate some of the acid reacts. So if you got 4 millimoles and then you're adding 9.5 milliliters of 0.40 molar KOH, then that comes out to 3.8 millimoles. Do the math, 3.8. It's your limiting reagent. That's going to demand the 3.8 of your acid reacts, which means that it forms 3.8 of the conjugate, 3.8 of the conjugate. The amount that reacts is going to form the conjugate. Now we have the conjugate is 3.8 millimoles. The acid, 4 minus 3.8, 0.2 millimoles. Okay, it's all sitting in the same volume. It's all sitting in the same volume. That volume would be 19.5 milliliters. Why? Because you had 10 originally and you're now adding 9.5 milliliters of titrate. This is a buffer. Why is it a buffer? Look, they're both present in the solution. I can just go to this equation right here. pKa plus the log. My conjugate is 3.8 over 19.5, but why divide by 19.5? Because I'm also going to divide by 19.5 in the denominator, so they cancel each other. It's just 3.8 over 0.2. And if you do that, okay, you should get a pH of 8.73, and here it is right here, okay? Using the Henderson-Hasselbalch equation. I probably rounded off too much in one of these, but hey, that's pretty close, okay? You're gonna get that. As long as you have both pairs present in solution after the stoichiometry, you've got a buffer, go straight to the Henderson-Hasselbalch equation. Go straight to the Henderson-Hasselbalch equation. It'll save you grief, okay? So now I got 3 points. I got 3 points right here. Let me clear this. There it is. That's a 95%, that's a 50%, and that's the initial. Now we have the equivalence point. We have the equivalence point. At the equivalence point, this 4 millimoles now converts completely over to the conjugate. But the volume is now 20 milliliters. So at the equivalence point, 100%, the 4 millimoles of acid converts over to the 4 millimoles of conjugate. The 4 millimoles in 20 milliliters, total volume. That's total volume. You need the total volume here because you need to know the concentration in molarity. But once you have that, okay, once you have that, then just do this. Hydroxide ion concentration is equal to the square root of the Kb times this concentration right there. Because all your acid is now the base. And that's just a weak base problem. That's just a weak base problem. Okay, it's hydrolysis. So let me show you that calculation real quick. Here it is. This is 4 millimoles, and if you divide it by 20, that's 0.2 molar. Now, I gave you the Ka. How do you calculate the Kb? Remember, the Ka times Kb equals Kw. So you can use that. And so that's what I will have right here. This is my Kb. Let me clear this for you. Kb equals Kw over Ka. That happens to be, what is that value? 2.8786 times 10 to the minus 7. And what I did here was, well, let's figure it out. Hydroxide ion concentration is equal to 2.86 times 10 to the minus 7 times 0.2. Let's see what we get when we do this shortcut. So I'm going to take 0.2, multiply it by 2. Remember, this is Kb. Okay, that's Kb. 2.86 to the 7 negative. Multiply that out, and then take the square root of that. I have something of 2.39 times 10 to the minus 4. That means my POH is equal to, take the negative log of that, 3.62. But if you plot this in your graph, you're going to get a titration curve that looks like this. Like I said, it's going to drop. Remember, this is POH. You got to subtract 14 from that. And now my pH is 10.37. 10.37. Hey, that's pretty close. Okay, that works. That works. I skipped all of this. I was able to use that just by using that equation. Just by using that equation. Finally, okay, finally, here it is. We got this 10.38. Okay, finally, what happens when we have excess? Well, this is the amount of base that did not react, 0.2. What is the total volume now? The total volume is going to be 10 from our analyte plus 10.5 from the titrant I add is 20.5 milliliters. So the concentration of that excess base that was unreacted is 0.2 millimoles over 20.5 milliliters. That concentration of hydroxide is just 0.2 divided by 20.5. That's 9.76 times 10 to the minus 3. That's my hydroxide ion concentration. If I take the negative log of that, no equilibrium involved now. That's just hydroxide directly. If I take the negative log of that, that happens to be 2.011, okay? But remember, that's POH. In order to get pH, you got to subtract 14 from that. That's 11.99. Look at the answer right there, 11.99. 11.99. Now, this chemical right here, that's a base. So that base will also produce hydroxide. But I'm going to show you in this calculation up here that the amount is so minute, you ignore it. So I'm going to clear this. This is the calculation for how much the conjugate produce in terms of the hydroxide when it does hydrolysis, because remember, you're going to have the conjugate in that solution. Look at the amount that you actually get. You actually have to solve this using the quadratic, and that concentration is about 6.64 times 10 to the minus 6. 6.64 times 10 to the minus 6 versus 9.76 times 10 to the minus 3 from the excess hydroxide. You ignore the contribution from this. You ignore that because it's not significant. It's not. So you have our last point, 11.99. Now you connect the dots. You connect the dots. Don't do this, okay? That's not a titration curve. It generally is going to be level right in the buffer region, and then it takes a steep incline right around the equivalence point. Okay, takes a steep incline. So think about that. This is, I know I went pretty quick, but it's not something new. It's what you guys already know. Okay, and I'll wrap this up probably first 15 minutes on Monday. But you guys know how to generate titration curve. Do the shortcuts that I have here, because it'll save you a lot of time. Okay. So sorry, it's 6:20. That's all I have for today. This, as soon as I find time between grading and doing other things, I'll edit this video and post it so you guys can review again some of the things that we talked about.